Welcome to qnawire.
All right, so we have got the dehydration of cyclohexanol. And I mean, there was no reaction shown. I'm guessing, I don't think the whole problem got uploaded, so I don't have all the information you do. But it sounds like what they are saying is that some acid, I'll say H2SO4, was used, maybe some heat. So the dehydration would have proceeded as follows. Right. Something like that. Okay. So what is the function of the acid used in the reaction? Right. And I think, what I would point out is that to do an elimination reaction, you need a good leaving group, right? But OH is not a good leaving group, right? Because when it leaves, it's OH minus. It's not very stable. And it's really hard for OH minus or OH to act as a leaving group, right? But the first step in a dehydration reaction like this is protonation of the alcohol to give water, right? And water is a good leaving group, right? So that's the purpose of the acid, is to protonate the alcohol. To protonate the alcohol to make a good leaving group. Okay. Why is only a small amount needed? Right? Okay. So let's consider this real quick. Let's consider any old acid, right? Which, if it's aqueous, is going to give us H3O+. Actually, I'm going to write this a little differently. Okay. So we'll just go through this mechanism real quick and explain why you don't need very much acid, right? So like we said, there's the protonation. Now we have OH2+ up here. And we also generated water from our H3O+ in this last step. So that water can come in. It's going to deprotonate the carbon, form the double bond while water leaves. Right? And the product of this, well, okay, so this was a water that came off, right? Okay, so we're going to have H2O. But we're also going to have, right, there was this water that came in and stole this proton. Okay, so we're going to have regenerated the acid we started with, right? It's a catalytic acid because when it's all is said and done, we regenerate the acid, right? So you only need a small amount because it doesn't get consumed. The same acid, the same H3O plus or H2SO4, whatever acid you use is getting regenerated at the end. So you don't need very much. Because the acid is used catalytically. It is regenerated. Okay, which direction would you expect the equilibrium to shift if... Okay, so let's just write the overall reaction in equilibrium form, right? Okay, so we have... Okay, and this is in equilibrium with cyclohexene. So we have cyclohexanol in equilibrium with cyclohexene and water. Okay, that's our equilibrium. Reactant is the cyclohexanol. The product is cyclohexene and water. Okay, what would happen to the equilibrium shift if cyclohexene was distilled off as it was formed? Okay, so that's saying we're reducing the amount of cyclohexene. So if we reduce the amount of products, the equilibrium is going to shift in a direction to increase the amount of products. It always counteracts whatever we do. Okay. The one way I'll quickly sort of conceptualize this is I like to think of it as like, imagine we have a sort of system in which we've got water. And a series of like this little U-shaped system, right? We're at equilibrium, okay? And then we have a drain. And we drain some of that water out, right? And so the water level decreases. Okay. Now the question is, which direction will water flow if we drain some water from the right-hand side? The answer is that water is going to flow to the right, right? Until we can even things out again and get a new water level, which is even. Right? That's just the way the pressure is going to work. Right? It wants to re-establish the equilibrium height of the water. Right? So if we remove water from the right-hand side, then water will flow to the right-hand side to replenish it. And the same thing is true for this equilibrium. If we remove product from the right-hand side, then water will flow to the right to replenish it. Okay, what if a large excess of water is added? Right, so we're going to add water to the right-hand side. Well, hey, this works with this example too, right? What if we've got this water level and I pour a bunch of water in, okay, and I bring the water level up to here, right? Which direction is water going to flow in this system to counteract that? It's going to flow to the left to even things out again, right? Same thing will happen here. If we add water, the equilibrium will shift to the left to counteract the water we added. Okay, what if the quantity of phosphoric acid present was doubled? Oh, okay, so it was phosphoric acid, not H2SO4. Okay, well, what do you think? Does the quantity of acid matter here? Does it matter how much acid we have? Well, consider what the rate limiting step in this is. It's probably this water leaving, right? The protonation is not the rate limiting step. It's a really easy reaction to handle, right? If this is the rate limiting step and acid is not involved in that step at all, then it shouldn't make a difference in the in the rate determining step. It shouldn't change the speed of the reaction. But what about the equilibrium? Will it push the equilibrium in either direction? Well, consider that I could add H3PO4, right, here. But remember, it's regenerated in the end, right, H3PO4, right? So it's a reactant and a product, right, because it's catalytic acid. We regenerate the acid when the reaction is done. So we typically don't write these here. And the reason for that is that you can't change the reaction by increasing the concentration on the left-hand side. It won't actually affect the equilibrium the way that changing these other reagents will, right? So adding acid, doubling the amount of acid won't do anything. It won't double the reaction rate, and it won't push the reaction forward or backwards, right? Because if we add acid, we can't just add it to the reactant side. We're also adding it to the product side. Right? There's nothing different about this acid and this acid. It's the same acid, and they're all in the same beaker, right? So, we will test for the presence of unsaturation by adding small sample of elemental bromine. What product formed? Okay, so the reaction of any alkene with Br2 gas bubbled through the solution, right, is that we get a dibromoalkane. Okay. So the product formed, if we do this with cyclohexene, is the following. Okay. Bromine adds across the double bond. And then the next question, why does positive reaction result in the solution of bromine colorless becoming? Okay, something went wrong with the transcription of that question. But basically, I think what they're getting at is that if you've got a beaker and you've got a tube, and you bubble bromine gas through your solution, the solution will turn brown. The bromine turns the solution brown, right? If you add enough cyclohexene, right? Recall that the cyclohexene doesn't just turn into the dibromo compound. I mean, it does for sure, but part of that is consuming the bromine, right? We're losing bromine when the reaction goes forward. So the solution will turn colorless if we add enough cyclohexene.